This lesson is for factoring trinomials using the rectangular model instead of the algebra tiles. When we used the rectangular model before, we were given the dimensions of the rectangle and we were looking for the inside part, the area. This is the opposite. We're starting with the area and we're trying to come up with what the dimensions of the rectangle would be, so we're looking for the outer edges. If we have an area, like in the first example, where we've got x squared plus 7x plus 12, thinking in terms of tiles, we always put the squared terms in the upper left-hand corner. So in the rectangular model, I've placed an x squared in the upper left-hand corner. We always put the small squares, the small red squares, in the lower right-hand corner. That's why I've placed the 12 there. Now, the other two parts of the rectangular model that my arrows are pointing to, those are the two areas that have to combine together to give us the 7x's. Without any other information, there's lots of choices we could pick there. We could pick a 6x and a 1x, a 5x and a 2x. We could pick a 10x and a negative 3x, as long as it combines together to give us a 7x. The hint for the rectangular model is if you look at the two items that you've already placed in the rectangle model, so the x squared and the 12, if you multiply the two of them together, it gives you a 12x squared. So the numbers and the letters that you have to place in the remaining two boxes have to have the property that I've written down here at the bottom. You have to select two items that will multiply to a 12x squared, the same thing as the other two numbers multiply to, but you have to also pick ones that are going to add to a 7x. There's only one option that'll work, and in this particular case, we would have to use a 3x and a 4x. Now, the 3x and the 4x make up the two boxes in the rectangular model where the arrows are pointing. Doesn't matter which gets the 3x and which gets the 4x. So I'm going to put the 3x here and the 4x here. The four boxes altogether make up the original area. We have to find out what the dimensions are, so what the edges are going to equal to. First step is going to be a greatest common factoring step. I like to start with the two items that are in the top row, and I look for what their greatest common factor is. In this case, it's x. I place the x in the first position for the dimension. To fill in the other parts of the dimension, I use logic. In order for this to be an x squared, then the product of the x that I've written down and the blank spot up here have to give me the x squared. That tells me my only option is to put an x in that position. If I want to find the value down here, then the logic is that what I place here, when multiplied by the x, has to give me the result of 4x. Therefore, I know I have to put a 4 here. To get the box up at the top, the logic is that this item multiplied with this x have to give me 3x, which means I know I have to have a 3 here. The last section is a double checking section. The 12 is created by multiplying this item and this item together, so we can double check that it actually works. Once I've completed the edge along the left-hand side and the edge along the top, those become my factors. So the x plus 4 is one of my factors, and the x and the positive 3 becomes my other factor. So when I want to factor an x squared plus 7x plus 12, I need to come up with the multiplication statement that, if expanded, would equal the original trinomial. So what I have here is the factored form. Now, we'll go through a couple more examples that you'll want to copy into your notes, and then you'll try some yourself as well. So looking at the bottom of that page, we've got a couple other situations. Now, when you're trying to factor the b squared plus 9b plus 20, we're going to fill in two parts of the area. I know that the b squared is going to be in the upper left-hand corner, and the 20 is going to be in the lower right-hand corner. The other two boxes have to combine together by addition to give me the 9b. So I'm looking for numbers and letters that will add together to give me a 9b. Again, there's too many choices there. So we're also going to combine that with a multiplication. If you multiply together the two items that you filled in, you get a 20b squared. Therefore, the numbers that I pick for the remaining two positions have to multiply to a 20b squared and have to add to a 9b. That limits my choices down to one option only. The option in this case, and I can put them in the rectangle in any order, is that I'm going to have a 4b and I'm going to have a 5b. Those are the only options that will add to a 9b and multiply to a 20b squared. To finish the factoring, I look at the top row, I take out the greatest common factor, which happens to be a b. To get the b squared, this b has to multiply by what I put here, so I know that that's going to be a b. To get the 5b, then the b at the top has to multiply with this section to get a 5b. I need to put a 5 there. Here, I have to find something that's going to multiply with the b to get 4b, therefore the 4 is there, and to double check, the 4 when multiplied by the 5 gives me the 20. That tells me that one of my dimensions of the rectangle is a b plus a 5. The other dimension of the rectangle is b plus 4. Together, written as a multiplication, equals the factored form of the original polynomial. So we're using the same logic as the algebra tiles without actually touching the algebra tiles. Now, for the next one, we've got a 4x squared plus a 20x plus a 9. Place the 4x squared and the 9 first. Multiply the two items together that you've placed in the box. They're going to multiply together to give you 36x squared. Because the middle term of the original polynomial was a 20x, then the two boxes that I have left to fill in have to add to 20x, and they also have to multiply to the 36x squared. Might take a little longer to figure this one out because the numbers are larger, but you will eventually find that if you picked an 18x and a 2x, it satisfies the conditions of the multiplication and the addition. I put the 18x and the 2x in two boxes. Again, doesn't matter where you put the 2x, doesn't matter where you put the 18x. So if I put a 2x here and an 18x here, you go to your first row and you look for what is the greatest common factor. Now here it's not just an x, it's a 2 and an x. 2x goes here. Then logic to finish the rest off. These two have to multiply together to give me the 4x squared, meaning that I have to have a 2x here. These two have to multiply together to give me the 18x, so I have to have a 9 here. This part with the 2x have to multiply together to give me this 2x, so I have a 1. And then my double check is that the 1 has to multiply with the 9 to get 9. Therefore, my factors are a 2x plus 9 and a 2x plus 1. If you want to double check, you have two options. You could do the distributive method here, multiply out your factors, see if they match the original polynomial. Or you can pick a number for x, substitute it into the original polynomial to get a numerical answer, take your same number for x, substitute it into the factors, multiply what you get. If the answer that you get matches the answer that you got for the polynomial, then it's correctly done. I would just multiply this out using distributive method if you want to double check. Okay, so you might be thinking right now, easy. Find your two numbers, go from there. The next couple of examples are going to be a little more challenging because they're going to have negatives involved. So if we go to the next page and we look at the examples at the top, same procedure is going to apply. I place the x squared, I place the 25. To fill in the other two parts, my numbers will have to multiply to the same thing that this diagonal multiplies to, 25x squared. And my numbers have to add to whatever the original middle term was, which in this case is a negative 10x, because these two boxes have to combine together to give me the negative 10x's. When I look at the numbers I have here, because I'm multiplying to a positive 25, I know that my numbers either have to be both positive or both negative. Since my numbers have to add to a negative number, I know that my two numbers have to be negative. In this case, a negative 5x and a negative 5x. Place those in and repeat what we've done before. Looking at the top row, I'm going to remove a greatest common factor of x. Logic now, because length times width is equal to area, these two have to multiply to give me the x squared. I have to put an x here. These two have to multiply to give me the negative 5x. I put a negative 5 here. These two have to multiply to also give me a negative 5x, negative 5 here, and my double check, the negative 5 and the negative 5 multiplied together give me the 25. This time, my factor has a subtraction sign in the middle in both situations. Now, your factored form can be left like this. If you prefer, you can write the factored form as a binomial squared. That's another acceptable way to write the answer. Next example, two negatives are involved, a little bit more challenging. You place the square tiles first, the 6b squared. You place the small square tiles next, the negative 3. When you multiply what you've placed, you get negative 18b squared. So the other two parts that you have to fill in order to find your dimensions of the rectangle or your factors for the polynomial, those two boxes have to multiply to negative 18b squared, and they have to add to whatever the original middle number was. In this case, negative 7b. Because your numbers that you select have to multiply to a negative number, you know that one of them has to be negative and one of them has to be positive. In order to get two numbers that multiply to a negative 18b squared, and add to a negative 7b, the only option is if you have a negative 9b and a positive 2b. Those are the only numbers that satisfy both conditions. Again, you're going to place those numbers into the remaining places in your rectangular model. You would have negative 9 rectangular tiles there, and you would have positive 2 rectangular tiles here. Now you have to look for the factors. Top row, if you take out a greatest common factor, you're going to be taking out a 3b. Because there's a 3b in that part of the dimension, the items we place here have to multiply with the 3b to get the 6b squared. Has to be a 2b. Because you've placed a 2b up here, what you place in this open area has to multiply with the 2b to get 2b. Therefore, you have to put a 1 here. To get the negative 9b, you're multiplying the 3b by something. We have to use a negative 3. And then our final double check is the negative 3 times the 1 gives us a negative 3, so we know that we've satisfied all 4 sections of the area. One of my factors is a 3b plus a 1. The other factor is the 2b minus the 3. Again, to double check, you multiply your factors together using your distributive method to see if you actually get the original polynomial. Okay, 2 more examples to go. These ones are going to have an extra step that we have to include. If we go to the bottom of this page, it tells you here that if the trinomial has a greatest common factor, factor it out before starting the rectangular method. If I look at question E, I can see that all 3 terms are divisible by 3. Therefore, I can take a 3 out as a greatest common factor, leaving me with an a squared plus a 5a minus a 14. Now, when I factor with the rectangular model, I'm going to ignore the 3. What I'm going to do with the 3 is put it at the bottom as a factor. Following the 3, I'm going to have 2 sets of brackets, but I haven't found out what to put in the brackets yet. So I ignore the 3 when I'm working with the table. I place just the a squared in the large square tile box. I place the negative 14 in the small square tile box. The product of those two is a negative 14a squared and the addition part doesn't come from the original middle term anymore. It comes from my factored step. So I have to find numbers and letters that when I multiply them together I get the negative 14a squared, and when I add them together I get the 5a. That's going to give me one option only, which in this case, to satisfy both conditions, I would need a 7a and a negative 2a, which I place in the 2 open areas. 7a, negative 2a. Now I factor. Greatest common factor here is an a. That's my starting point. I have to find what multiplies with an a to get an a squared. I have to find what multiplies with an a to get a negative 2a. I have to find what multiplies with an a to get a 7a. and I double check that the 7 and the -2 give me this number. My factors in this case, there are 3 of them. I have the original 3 that I factored out. From the left-hand side of my rectangular model, I have the a minus 2. From the top side of my rectangular model, I have the a plus the 7. Again, if you want to double check, you can substitute a number in, or you can multiply to expand, gather like terms to see if it matches the original. For question F, the first step is to look for a greatest common factor. So here, you want to make sure that you are selecting the largest factor, because 2 is a factor for all 3 terms, 4 is a factor for all 3 terms, but 8 would be the greatest common factor. If I take out an 8, I'm going to be left with a 2p squared minus a 7p plus a 3. We factored it completely, or we factored with the greatest common factor. Now, I want you to take a couple of minutes, attempt to finish off the factoring by substituting into the rectangular model, remembering that your answer at the end will still have the 8 and will have 2 sets of brackets. Okay, take 2 minutes, see if you can complete the factoring. Hopefully you were successful with that. You place the 2p squared, you place the 3. That means that the 2 remaining boxes have to satisfy the conditions that they have to multiply to a 6p squared. They have to add to this middle term, -7p. Again, because we're multiplying to a +6, we know that our numbers have to either both be negative or both be positive. In this particular case, because they're adding to a negative number, the numbers have to both be negative. We end up using a -6p and a -1p. You can write the -1p just as a -p if you prefer. So I'm going to place the -6p here and just a -p at the bottom. The greatest common factor in the top row is both a 2 and a p. To get the 2p squared, I'd have to multiply the 2p by a 1. Sorry, a 1p. So I'm just going to write it as a p. To get the -p down here, I would have to multiply the p at the top by a -1. To get the -6p, the 2p would have to be multiplied by a -3, and then my double check is that the -3 times the -1 is equal to the +3. Here's one of my binomial factors, 2p minus 1. Here's the other binomial factor, p minus 3, and then I still have to put the monomial factor of 8 in front that I removed at the beginning. Hopefully, with those examples, you understand the concept of factoring trinomials, with a rectangular model, always look to see if you can factor out a greatest common factor first and then go to the rectangular model. For the remaining time that you have in class, the next page is going to give you some practice questions from two different pages, page 166 and page 178. Now, I have already picked and chose certain questions, so I want you to please attempt all of the questions that are on the list. Okay, good luck with those and have a good day.